Hello everyone, welcome to John Sitter's Betaflight Pit Tuning Tutorials. Today we're gonna spend about 5 minutes to learn how to use step response graph to find the right PD gain for your quad, which are probably two of the most important parameters for a quad. First, what is PD balance and why does it matter? To answer this question, let's first answer why we want to tune our quad. There are two main reasons. Number one, when we move our sticks, we want the quad to do what we ask it to do, right away with no lag if possible. Number two, when we are not moving our sticks and there are external disturbances, for example wind turbulence, we want the quad to resist to those disturbances. Prop wash situations, for example, is one of these external disturbances. For Betaflight, PD balance is mostly for number one. Here is how it works. When we move our sticks, the P component of the pit loop is the factor that pushes the quad into the move, whereas the D component is the factor that prevents the quad from moving. In fact, in Betaflight, D is always a factor that prevents the quad from any kind of movement. We'll go into more details on this in later tutorials. We need a good PD ratio to achieve good response from our quad. In the beginning of our stick move, we mostly need P to kick the quad into the move and don't need much D. But at the end of our stick move, we need D to stop the quad from further movement to avoid overshoot. If PD ratio is too high, the quad will move more than what we command it to do, thus resulting in overshoot. If PD ratio is too low, the quad will be sluggish to do what we command it to do. With that, let's take a look at how to use John Sitter's Step Response Overview feature to find the best PD ratio for your quad. Step number one, clear out your black box storage and set the black box recording speed to 1 kHz. We don't need to worry about the debug mode right now because step response only needs the signals that are provided by default. Step number two, put in the following settings to make sure we get the best step response data. Use default PD as a starting point. For regular 5-inch, 35 to 45 should work. If the quad doesn't fly well, turn both down to 30. Also turn off feed-forward by setting the value to 0. And turn off absolute control by setting the gain to 0. Also turn off D-min. And also turn I-gain down. For normal 5-inch, 30 to 40 is good. Also, turn off TPA by setting the value to 1.0, as shown in this screenshot. Then, fly the quad and let it record some logs. 1 minute of flying is usually enough. You can use Brian White's basement tuning method, where you basically just hover the quad and quickly move your roll stick left and right. Do it for 1 minute. Then, plug in the quad to the computer. Enable black box mass storage mode. Then you can access the flight controller's black box just like a U-disk. Then go to dronesitter.com and use DroneSitter to open the black box you just generated. Then use DroneSitter's Step Response Overview feature to analyze. Click on the Step Response Overview button at the top. In 1 or 2 seconds, it should generate the step response graph for all roll, pitch, yaw axis. You should see 3 graphs that look like this. Since we only moved the roll, we only need to look at the roll axis. You can also do the same to other axes, but if the pitch and roll are symmetric, they can share the same PD ratio. The x-axis of this graph is time in milliseconds. The y-axis is the drone's response. To understand the graph, you can think of at time 0 milliseconds, you ask the drone to reach to state 1, for example, asking the drone to a certain angular velocity on the roll axis. This line then plots how the drone responds to your command, which is the actual drone's angular velocity. For example, in this graph, at time 0, the quad starts to react to our command. The angular velocity starts to increase. At around 10 milliseconds, it reaches to the angular velocity we ask it to do. But since the PD ratio is not set right, it overshoots, end up being 1.8 times the angular velocity we ask it to do. And then you realize that it overshoots too much, and then comes back down. This graph is a good example for P being too high, thus it swings several times before it converges. The following is what a good PD balance looks like. It overshoots only a little bit and converges really fast. The next step is to adjust the PD ratio and go back to step 3 and iterate. If it looks like the PD ratio is too high, lower P, by 5 for example. Otherwise, increase P until your graph looks similar to the good PD balance. Once you find the perfect PD balance, you can increase P and D up with the ratio kept until you get oscillations. This is then the perfect value for P and D. This step makes sure your quad can resist disturbances well. We'll get into more details on this in later tutorials. Okay, this is basically how you tune the P and D gain for your quads, which are two of the most important tuning parameters. This will help the quad better track your stick input and overcome any prop wash or turbulence. Alright, this is John Sitter. I'll see you next time.